So let's talk about what's called mole-to-mole stoichiometry. And the whole point of this is to use moles of one part of your reaction, whether it's your reactants or your products, to predict the number of moles that you'll get of another reactant or a product. So we're looking at these mole ratios. Now, I have on the board behind me a balanced chemical reaction. So we're reacting 2 magnesiums with an oxygen to produce 2 magnesium oxides. Now, we know that we can draw particle diagrams of this. So if I have magnesiums as squares and oxygens as circles, I'm going to have 2 magnesiums plus an O2 to produce 2, oops, not M, 2 magnesium oxides. So that's what my particle diagram would look like for this balanced chemical reaction. Now, we also know that these coefficients can tell us moles. So we know that we can have 2 moles instead of 2 particles of magnesium reacting with 1 mole instead of 1 particle of O2 to produce 2 moles of magnesium oxide instead of 2 particles. So we can think about these in terms of individual particles, or we can look at it in terms of moles. And for this unit, for these types of examples, we're going to think about those coefficients in terms of moles. So notice my number of either particles or moles corresponds to the coefficient in my balanced chemical reaction. So let's look at an example. So in my first example, it says if you have 3 moles of iron, how many moles of copper will be produced? And here's my chemical reaction. So I have iron plus copper 2 sulfate, producing copper and iron 2 sulfate. The first thing I want to do is check to make sure that it's balanced. So I have 1 iron, 1 copper, 1 sulfur, 1 sulfur, 4 oxygens, 4 oxygens. So my reaction is already balanced. So I know that I'm starting with 3 moles of iron. And I need to know what the ratio is between iron and whatever I'm looking for. So I'm comparing iron to copper. Now I know, according to this, so my coefficients are 1s, that I will get 1 copper for every 1 iron. My coefficients tell me that ratio. So instead of just saying 1 copper and 1 iron, we're working in moles, so I'm going to make this 1 mole of copper to 1 mole of iron. So this means for every 1 mole of iron I use, I'm going to produce 1 mole of copper. It's a 1-to-1 ratio. So if I'm using 3 moles of iron, that means if I do 3 times 1 divided by 1, I'm going to get 3 moles of copper. So since this is a 1-to-1 ratio, we're going to have equal amounts of copper produced as iron used in this reaction. So in this example, we compared a reactant to a product, which is often what we're going to do in lab. You can also look at this by comparing 2 reactants, and that's what our next example is going to look at. So our second example says, if you have 2.5 moles of zinc, how much hydrochloric acid will you need to react all of the zinc? So if we think about this practically in lab, you have some zinc, in this case 2.5 moles, and you're going to react it with hydrochloric acid, and you want all of that zinc to react. Well, instead of just pouring in random amounts of hydrochloric acid, it's more efficient if you actually figure out how much that you need. So let's do that. So if I'm starting with 2.5 moles of zinc, again, I'm going to look at my ratio of my coefficients. So I have 1 zinc to every 2 hydrochloric acids, which means for every 1 mole of zinc, I need 2 moles, 2 moles of hydrochloric acid. That's because when this balances, I see that I need a 2 in front of my HCl to make my chemical reaction balanced. So that tells me that for every 1 mole of zinc, I'm going to need twice as much hydrochloric acid. So now if I do the math, if I have 2.5 moles of zinc times 2 divided by 1, I get 5 moles of hydrochloric acid. So instead of just pouring in random amounts of hydrochloric acid, I can actually measure out 5 moles, and with hydrochloric acid, I would probably measure out in milliliters, but that's something we're going to talk about later. But I know that I need 5 moles of hydrochloric acid minimum to react all 2.5 moles of my zinc.